morning, students. We'll now continue with the lecture. So now in the chapter 1, there is steady current and magnetic field, where it's defined a magnetic field using Biot-Savart's law, and we try to find out magnetic field due to the wire, straight wire, then the coil. We also found the expression for the magnetic field of a current carrying wire using what is called as a Ampere's circuital law. Now, let us little recall electrostatics. In the electrostatics, we had used Coulomb's law to calculate electric field. Now, using the Coulomb's law, the calculation of the electric field was easy for a single charge, pair of the charges, then 3 charges. But as the number of discrete charges increased, then there was a difficulty in the calculating the electric field, because the electric field is a vector quantity. Then we had given another law, what is called as the Gauss's law, and with the help of the Gauss's law, calculation of the electric field was very simple, but one can calculate the electric field for a symmetric charge distribution. The problem of calculating electric field, there is a difficulty because electric field is a vector quantity. So then in electrostatics, to calculate electric field, then we had defined a quantity called as a potential, and the potential or the quantity which was defined, which is a scalar quantity, and calculation of the scalar quantity is comparatively simple. Then defining this potential, we had seen how to find out the electric field. Electric field was a negative derivative of the potential, or in 3 dimension, electric field is equal to minus grad phi. Phi is a potential. So one could calculate the electric field easily, because calculation of potential is easy. The potential is a scalar quantity. So from the potential you can calculate electric field minus grad phi. Then direction of the electric field also found by drawing what is called as the equipotential surface. If you know the potential, then you can calculate the potentials, and we can join the surface having all the at every point the potential equal, and the direction of the electric field could also be found. Now in same way, in magnetism, we will define here a potential, because to calculate a magnetic field is not easy for every circuit. So we define a potential, but in the magnetism we have to define 2 types of the potentials. One is a vector potential, other is scalar potential. 2 potentials are to be defined, or we can define a vector potential and a scalar potential. So we will try to define this vector potential and a scalar potential, and then knowing this vector potential and a scalar potential, we will be able to calculate a magnetic field. So idea behind defining the potential is to find out or calculate a magnetic field. Then we define a magnetic field of a distant circuit. See, when we say circuit, it is like a magnetic dipole. See, in the electrostatic we defined a point charge, then a pair of the charges, a dipole. Electric dipole has some significance. Now in magnetism, especially when a circuit is there, the circuit is behaving like a dipole because one phase acting like a north pole, other phase acting like a south pole. So it is behaving like a dipole. So just like in electrostatic we found the electric field due to the dipole at a very large distance, in same way we will find the magnetic field of a distant circuit. So these are the things we are going to do. Now, first let us see what is the magnetic vector potential. Magnetic vector potential. See, now in the electrostatics, we first define the electric field. We find the electric field, and to calculate the electric field, we define the potential. We define the potential, and it was shown that the negative gradient of the potential is nothing but the electric field. Electric field was the negative gradient of the potential. Now from this we are able to show this relation. See, we are able to show this relation. There is a reason for that. In fact, we derived this by saying that the curl of electric field is equal to 0. Curl of electric field is equal to 0. See, we have proved this in the first term. We showed that curl of electric field is 0. That's why we are able to write electric field equal to minus grad of phi. So we are able to write electric field as negative gradient of some scalar quantity, and that scalar quantity was called as a potential. So this we are able to do because of this term. But in magnetism, we cannot write vector B equal to minus grad of phi. We cannot write vector B equal to minus del of phi. We cannot do it because the curl of magnetic field is not 0. See the curl of magnetic field. It is equal to mu naught J, vector J. We have proved this. It is Ampere's circuital law. This is Ampere's circuital law. We have proved it. So we cannot because curl of gradient, curl of the magnetic field is not 0. Mu naught is some quantity. J is some quantity. The vector J is a current density. So current density is 0. That means current is not flowing. So this curl of B cannot be equal to 0. So since the curl of B is not equal to 0, so it is not equal to 0. So curl of B is not equal to 0. We cannot write vector B as, see, we cannot write like this. It's not possible to write vector B is equal to minus grad of phi. This we are not able to write it. So we cannot write it because curl of B is not equal to 0. If the curl of B was 0, then we will be able to write vector B equal to minus grad of phi. Okay. So curl of B is not 0. It is some finite quantity. But one more thing is, we have proved, last time we have proved, divergence of B equal to 0. See, del dot B equal to 0. That is called the Gauss's law in magnetism. This equal to 0. Now let us see what is the consequence of this. Say, we know that, see, this is a divergence of the curl. Divergence of curl of any vector is 0. This we know that divergence of curl of any vector is 0. So divergence of curl is 0. Because divergence of curl is 0, let us say that we will find some vector A so that this the curl of A is equal to B. See, this is 0. The curl of B equal to 0. So divergence of B equal to 0. So divergence of B equal to 0. So since divergence of B equal to 0, we write this B as curl of A. A is some vector that we have to find out. Okay. So now we are able to now write the B as curl of some vector A. So that is because a divergence of the vector B is 0. Since divergence of vector B is 0, then B can be written as curl of A because divergence of curl is 0. This is a property of the divergence. So we can write B equal to the curl of A. And just like since we have written E equal to minus grad phi in same way, this A, vector A is called as a magnetic vector potential. Okay, so now we are able to define some potential which is a vector quantity. Unlike in electrostatic is a scalar quantity. Here potential can be also vector quantity. So by using this property that curl of B is not equal to 0, but divergence of B equal to 0, we are able to write vector B as a curl of A. Okay, so we define here what is called a vector potential vector A. So now we have to find out what is that vector A. For a circuit, we will find out what is the vector A. So once you know the vector A, then you can find out curl of A, then that is a magnetic field. So the many times what happen is directly to calculate the magnetic field is difficult, but we can find out this vector A, which is called as the magnetic vector potential, and finding the curl of A, we can find out that magnetic field. So we will able to get the magnetic field. Now this definition, vector B equal to del cross A. Then one more thing is that Ampere circuital law. See, Ampere circuital law, this curl of B equal to mu naught J. So both should be satisfied. So B should be equal to curl of A, and the curl of B should be equal to mu naught J. This should be also satisfied. So in this case, we take this equation, the B equal to curl of A. Then this is a vector triple product. We have found, we have defined this in the first term, that A cross B cross C, it is a vector triple product, is a gradient of divergence of A minus del square A. Okay, but in the we have used this expansion for the vector triple, this vector triple product. But what we'll choose here is, just to simplify, we'll choose that divergence of A is 0. Then what we'll get is minus del square A equal to mu naught J. So del square A equal to minus mu naught J. So this is like a Laplacian equation. This is a Laplace's equation. Okay, sorry, Poisson's equation. This is like a Poisson's equation. So this is like a Poisson's equation. Del square of the quantity equal to some finite value. Okay, so see, to define the magnetic vector potential, that vector B equal to del cross A, we have to take into account that del cross B equal to mu naught J and del dot A equal to 0. So these two conditions are required. So two conditions in order to get magnetic potential should be del cross B equal to mu naught J and del dot A equal to 0. Then we will able to write this B equal to del cross A. Okay, and see, it is simple here because it satisfies this Poisson's equation. So now in Cartesian components, see Cartesian components, x component, see this vector B equal to del cross A, and that Poisson's equation del cross Ax equal to minus mu naught Jx. So Jx is x component of current density. Del square Ay equal to minus mu naught Jy. Jy is the y component of the current density, and del square Az equal to minus mu naught Jz. Jz is the z component of current density. Okay. So now what happened is, we now compare it in the electrostatics. As I already mentioned to you, that many equations in magnetism are directly taken from the electrostatics by replacing by the corresponding quantities. And the reason for that is, the derivations in magnetic field are very lengthy and complicated. So what is done is, they can be derived, but it is very lengthy and complicated. So what we do is, we try to translate the equation in electrostatics into the equation in the magnetism. And we know that the del square phi equal to minus rho by epsilon 0. The del square phi equal to minus rho epsilon 0. This is also called the Poisson's equation. And then this phi equal to, see, phi equal to this 1 upon 4 pi epsilon 0 integral rho dV divided by modulus of R2 minus R1. So in comparison in magnetism, what we will do is, so this actually has scalar potential, we write a vector potential. So 1 upon 4 pi epsilon 0, we replace it by mu naught by 4 pi, here, mu naught by 4 pi. Then we write here volume integral. So instead of rho, we write J. See, here what happens is, this is the volume density, this is the volume density of the charge, rho dV. So this is the current density. So J dV1 divided by vector rho 2 minus vector R1. So this is the formula for magnetic vector potential. So here we have written this equation in comparison with the electrostatics, but actually it can be derived, but that derivation, it turns out to be a research paper. It is very lengthy. Okay, it is beyond the scope of your TY BSc books. So directly the equation is taken, and for any circuit, we will take this equation as a standard to find out the potential, magnetic potential of that circuit. And once you know the magnetic potential, we will be able to find out a magnetic field. Okay, so there is a physical significance of magnetic vector potential. So using the magnetic vector potential, we can find out the magnetic field. See, using the magnetic vector potential, we can find out the magnetic field. And this is used especially in what are called as the electromagnetic waves. This is used. So now what we do next is, so we have already defined this magnetic vector potential. If you are, we'll use this formula to calculate the magnetic vector potential. If you know the magnetic vector potential, you can find out the magnetic field. Just take a curl of A. If you find a curl of A, you will get the expression for magnetic field. Now we take a magnetic field of the distant circuit. Circuit, as you mentioned that circuit is a closed loop where the current flows, and this closed loop can be of different shape. We have taken the circular, but it can be of any shape. Now what happens is, the one face of this circuit is north pole, other face is south pole. So it is called the magnetic dipole. So every circuit is a magnetic dipole. Now just like in electrostatics, you have found out the electric field at a large distance from the electric dipole. So here we will find a magnetic field at a large distance from the circuit, magnetic dipole. So now here we will make use of this formula, which we have written by comparing in the electrostatics. Vector A equal to mu naught by 4 pi in volume integral J R dV1 divided by modulus R2 minus R1. So now here what we do is J D1 dV1. Actually there is no volume as such in the electrical circuit. So J D1, what is the J? Current divided by area. See, this J is a current by area. So current divided by area. Then dV1 is a volume. dV1 is volume. See this JdV1. The JdV1 is current by area. Current density is a current by area into the volume. Now, so now volume divided by area is length. Volume is 3-dimensional, area is 2-dimensional. What will get the length? So we write this as current into distance. See, I into the distance, because volume by area is a distance. So for a current circuit, so you can replace J dV by I dr. So what is that's what we have done here. So this magnetic vector potential at certain distance R2 is I we take outside mu naught I divided by 4 pi integral of dr1 by 1 by R2 minus R1. Now similarly, a similar expression also we have written in the case of the electrostatics also. Similar thing we have written for the electric dipole. Now we have this formula. We have to evaluate this. What is 1 by modulus R2 minus R1? It's similar to what we have done in electrostatics. If you turn your pages of the electrostatics, in the second chapter you will find it. So first we will find out what is 1 by modulus R2 minus R1. This is modulus R2 by raised to minus 1. It's very simple. Then what you do is you multiply and divide by 2. So 2 and minus half. Then this is a modulus, like modulus A square, vector A square. It's just like vector A dot vector A is A square. Vector A, so it is like this. Vector A dot vector A is that magnitude square, A square. So same thing is here. This modulus of R2 minus R1 square is R2 minus R1 dot R2 minus R1. So that is what we have written here. Then you expand this, but you take into account that is the vector quantities and dot product is there. So R2 dot R2, then here this R2 dot R2, then R1 dot R1, and this minus R2 dot R1 minus R2 dot R1, that is minus 2 R2 dot R1. Then next what you do? What we do here is r2 dot r1 is r2 square, just like vector a dot vector a is a square, r2 square. R1 dot r1 is r1 square. This is there. Then next what we do here is we take that r2 square outside. So when it is taken outside, 1 is here. Then here r2 square was not there, so we divide by r2 square. Here r2 was not there, we divide by r2 square. This is what we do. Next, we use the binomial theorem. So, use the binomial theorem. In binomial theorem, see, first of all, this r2 square raised to minus half is r2 raised to minus 1. Then this quantity, this quantity raised to minus half. So, this is like x and 1 minus x here, minus nx. Power comes as a multiple. See, power comes as a multiple. And some higher terms are there, which we are going to neglect later on. So, we don't write them. Then this 2 and 2 cancels, minus minus plus, you will get like this. So here, see, this we have found 1 by r2, so 1 plus r1 dot r2 by r2 square, higher terms are there, and this equation 1 we are going to substitute it. And what we do here is, higher terms we neglect because they will be smaller. They will be power, square, cube, fourth, then raised to 5. So they will become smaller and smaller. So we can neglect it with respect to 1. Because 1 is here, we can neglect it. Okay. So we substitute here. Here we have substituted 1 by r2 into 1 plus r1 dot r2 divided by r2 square and dr1. Then open the bracket. Open this bracket. So 1 by r2 integral of dr1 plus 1 by r2 cube integral r2 dot r2 dr1. Then this I you take outside. Then integral of dr1 is r1 and is the loop integral. So when you substitute upper limit and lower limit is same, so that's why upper limit minus lower limit will be 0. So it will become 0. So just the integral of a dx is x. But here loop integral means what? Upper limit and lower limit is same. So when you substitute upper limit and lower limit, it will get cancelled. So it will become 0. Okay, so it turns out to be the equation 2. So now let us evaluate this. This is equation 2. Now, to evaluate this means, this we are finding. First, we will try to simplify integrand. So, you take this triple product, vector r1 cross vector dr1 cross vector r2. We are using the formula for the triple product, vector product which you have found. And also, we find d vector r1, r2 dot r1. Then, this r2 is constant here. R2 is a constant because r2 is the distance of the point. Where you are finding it is a constant. R1 is a variable. So difference of this. So first term R1, the R2 is constant. So into the derivative of second term. Then derivative of first term. See, first term is R1 and second term is also R1. So here, what do you write? The derivative of first term into the second term. R2 is constant, so it will go as it is. Then what you do is you add this to equation. Now this equation and this equation we add it. So when you add it, you get this equation like this. And then we find this part. This is what we want. This is what we will simplify this. And this is what we want. See, this is what we want. dr1, r1 dot r2. This one here in the equation 2. We are interchanging this. This bracket, if you take here, dr1 into bracket r1 dot r2. Okay. Then so this we are substituting, and when you substitute this, see, this we have equation 2, and this we have found it, and we substitute here. Now next what happens is, in this term, integral of d of something and loop integral, so it will become 0. So this is 0, and it turns out to be like this: mu naught by 4 pi. We write I by 2, and integral of r1 cross dr1 and cross r2 by r2 cube. So this we take out of the integral because it is a constant. R2 is constant, R1 is a variable. So that's why it is taken out of the integral. So this is what we get. So this is what we found. This is the magnetic vector potential. Then this, in comparison with the electrostatic, this quantity which is given as a square bracket, we write it as a vector m, and similar to the electrostatic, we call it as the magnetic dipole moment. In electrostatic, we have defined what is called as the electric dipole moment. So here the corresponding quantity is called as the magnetic dipole moment. So now what we get here is that vector potential, and once you know the vector potential, we can find out the magnetic field. the curl of vector potential. So we write it like this: B del cross this. We can simplify further. So we can simplify it like this. Again, this triple product we can find out. Then this, in this case, del dot. This is a position vector, but constant position vector. R2 is constant, and divergence of the constant position vector is 0, and you get magnetic field like this. So we'll use the expression for the magnetic field in this form as well as in this. Okay, so from the magnetic vector potential, we can find out the magnetic field. Then let us go to what is called as the magnetic scalar potential. So we'll define also magnetic scalar potential. So there are two potentials. One is the magnetic vector potential, other is the magnetic scalar potential. Unlike in electrostatic, there is only one potential, a scalar potential. Here we have both type, magnetic vector potential and magnetic scalar potential. Both are useful. With the help of both, you can find out the magnetic field. In fact, magnetic vector potential is used for the circuits, current flowing the circuit producing magnetic field, that to calculate that magnetic field. Whereas magnetic scalar potential is used for the material. See, there are two things. In magnetism, there are two things. Magnetism can be produced because the current carrying wire. So there, to find out the magnetic field, we make use of magnetic vector potential. But material, like a bar magnet, is a material. So in the case of the material, we use the magnetic scalar potential to calculate the magnetic field. Now this is a differential from the Ampere's circuital law. Now here what we do here is, especially for the materials, see, we will be using this for materials, the current density can be made equal to 0. Current density can be equal to 0. In wire or open, current divided by area. So current flows in a straight path or in some path along the line. In magnetic material is not like this. Magnetic materials, it is different. See, the bar magnet, it also produces a magnetic field, but it is because of the material. And in the current carrying wire, it is producing magnetic field because of the current in the wire. In the material, there is some other type of current that we will see later on. So in the material, the current density will be equal to 0. So del cross B equal to 0. Del cross B equal to 0. And just like in electrostatics, since del cross B, just like del cross E equal to 0, we are able to write E equal to minus grad of phi. In the magnetism, since del cross B equal to 0, we will able to write vector B is equal to minus something into grad of phi. We write phi star. Now this phi star is called as a magnetic scalar potential. We introduce here mu naught because it is magnetism. Just like electrostatic, it is epsilon 0 here, mu naught. So this phi star is called as a magnetic scalar potential. So we'll see how to find out the magnetic scalar potential. Once you find a magnetic scalar potential, just multiplying, finding gradient of that and multiplying by minus mu naught, you'll able to find out B. One more thing is here, del dot B equal to 0. Gauss's law in magnetostatics. Then here we substitute B equal to minus mu naught grad of phi star. So this minus mu naught comes out. This is equal to 0. So del square phi star equal to 0. This is a Laplace's equation. So this phi also satisfies the Laplace equation. So by solving this Laplace's equation, we can find out phi star, magnetic scalar potential. If you know the magnetic scalar potential, you will able to find out the magnetic field. And that's what we are going to do. Okay. So this also we consider here, as we have found earlier. So this part, in case of the distance circuit, this equation we can use, and corresponding to this, that phi star for a distance circuit will be m dot r2 divided by 4 pi r2 cube. So that is the magnetic scalar potential. So by comparing this equation, we are able to write also the magnetic scalar, just like we have written the magnetic vector potential. Okay. So this magnetic scalar potential will be used to find out the magnetic field. Okay. Now this completes the chapter. This completes the first chapter. The study. This first chapter is the magnetic field, steady current and their magnetic field. That is chapter 1. And this chapter will be included for you for ISA 2. Now this ISA 2 I will be giving to you on coming Saturday. Coming Saturday, that is the 10th April, we'll have a ISA 2 on this paper. And it will be at 9 o'clock. So 9 to 9:45 you will have the IS, and that will be followed by the practical. So prepare this chapter. So you will have the ISA 2 and it will be offline. So when you come to the college at 9 o'clock on Saturday 10, you will be answering the ISA 2. Okay, it will be in offline mode. So question paper will be given, and on the answer book you will be answering it. Okay, so that is on the 10th. Detail I will send on this WhatsApp group. So with this I stop here. Thank you very much. Next time I will start with the next chapter. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.